Hello everyone, my name is Yu Lun Kuo from National Taiwan University. Today I'll be presenting our work, Robot-to-Human Construction Tool Handover Grasp Prediction for 6DOF Robotic Arm with Parallel Gripper. This is a joint work with my colleagues Guan, Xiong, Jacob Liang, and Jyun Liang. On construction sites, workers often waste time locating or handling tools, which significantly reduces efficiency. Meanwhile, robot-to-human handover offers a promising solution to automate the tool passing process while improving safety. However, grasping construction tools is particularly challenging because they vary greatly in shape and can be dangerous to hold incorrectly. Our motivation is to use robots not just to locate tools, but also to assist in organizing them and eventually hand them to workers safely and efficiently. Current robotic systems struggle in dynamic, unstructured environments like construction sites. Moreover, most existing grasp prediction models are designed for household items, not for construction tools, which often have sharp or irregular geometries. This poses a risk in robot-to-human interaction scenarios. To address these issues, we set three key objectives. First, build a 6DOF grasp pose dataset specifically for construction tools. Second, separate robot and human grasp regions to improve safety. Last, fine-tune a grasp prediction model and validate its effectiveness in simulation using Gazebo. This slide shows the framework of our proposed method, which consists of 4 parts: data annotation, scene generation, grasp prediction, and motion planning. We will begin by discussing the details of the data annotation step. Here is the data annotation process. We selected 4 construction tools: wrench, pliers, screwdriver, and safety glasses, and manually labeled every candidate grasp point as either robot or human zone. By introducing this new status field, we ensure the model learns where a stable grasp exists and where it is safe for a human to receive the tool. In this example, we can see the annotated 3D models on the right-hand side. And here is the original GraspNet label format, listing points, offsets, collision, and scores. We extended it by adding a new status field. Status can be human or robot, informing the downstream planner which grasps to reserve for the worker versus the robot. This simple addition lets us encode ergonomic and safety constraints into the datasets. For scene generation, we imported our tool models into Gazebo and captured 132 multi-view RGB-D images using an Intel RealSense D435. These images cover diverse viewing angles to improve robustness. The visualization shows examples of the RGB frame, corresponding depth map, overlaid tool label, and the resulting 6DOF grasp poses. Finally, we fine-tuned the GraspNet baseline model for 6DOF grasp pose estimation. We started with a learning rate of 0.01, halving every 5 epochs, and used a batch size of 4. By training on our extended dataset, with human-robot zones explicitly labeled, the network learns safe grasps. Next, we'll see how this improved accuracy translates into real-time handover performance. Once the grasp pose is predicted, we convert it into world coordinates. We use the RRT algorithm to plan a safe path for the robotic arm, execute the grasp, and return to the home position. This is our hardware setup and evaluation metric. We used a UR5 robotic arm fitted with a parallel gripper and captured top-down RGB-D data with an D435 camera. For evaluation, we define success rate as the percentage of trials in which the robot lifts the correct tool without any slip or collision. Here are our quantitative results. After fine-tuning, the average success rate jumped from 30% to 92.5%, with each tool showing at least a 40% improvement. The detailed results are shown in the table. We also measured computation times. Inference takes about 1.6 seconds, and motion planning takes around 10.4 seconds, for a total of roughly 12 seconds per grasp. This slide shows qualitative examples of our fine-tuned grasps. These images highlight how our model adapts to different tool geometries and achieves safe grasps. We did observe failure cases. For instance, the flat geometry of wrenches led to occasional slipping or collision. Low confidence grasp poses on pliers also caused slippage. These insights will help us refine our grasp filter strategies in the future. To summarize, we created a construction-specific 6DOF grasp dataset with safety-aware annotations. Our fine-tuned model achieved a 92.5 average success rate in simulation. This demonstrates the feasibility of robot-assisted tool handover on construction sites. The proposed method demonstrated reliable performance across the 4 tool types. With additional training data, we expected the model to achieve better generalization across a broader range of construction tools. Based on our findings, we propose the following. Expand the dataset to include more tool types and geometries for better generalization. Conduct real-world experiments to validate system performance outside simulation. Integrate ergonomic reasoning to improve the naturalness of handovers. Reduce total runtime by optimizing inference and planning pipelines. This is the end of my presentation. Thank you for listening.